Okay, this video is at the end of a long playlist that started out with the definition of molarity, and from there we went to the definition of bases and acids and how to calculate pH and what pH was and so on, and then we focused on neutralization reactions, and that's all led us to this point, which is to look and see how neutralization reactions can be used to do things, because quite frankly, that's what chemists do. We do things. And neutralization reactions are used extensively to do all kinds of different things that benefit our society, like in waste treatment management, soil pH in terms of farming, for example, even down to the production of antacids that people take in order to lower the acidity of their stomach acid. So what I want to accomplish in this video is to lay out the groundwork for the classic what's called a volumetric analysis utilizing a neutralization reaction in the laboratory. And this is a laboratory that is classic. You will encounter it in any general chem university level class, any high school chemistry class, and any advanced placement chemistry class. So let's get started. Now, the model reaction that I'm going to utilize here as my example is going to be the strong acid, strong base titration, or reaction between hydrochloric acid and sodium hydroxide that produces water and a salt. Now, I've introduced the concept of titration in previous videos. The viewer needs to remember that it's a general technique that involves the incremental addition of one reactant into another reactant. So the idea of titration is a general term for any kind of laboratory manipulation where we're adding one chemical incrementally into another chemical. So the term titration is not just specific to acid-base titrations. It's also specific to redox titrations and just about any other kind of manipulation that involves carefully adding one reactant into another reactant. Now, if you've been following my playlist, then you'll realize that for a titration, one of the requirements is that we physically isolate the two reactants from one another so that we can then incrementally add the one reactant into another. So in this example, what we're going to be doing is actually reacting a 0.2 molar solution of hydrochloric acid with an unknown molarity of sodium hydroxide solution. So I'll use a question mark for that. And we're going to locate the 0.2 molar solution of hydrochloric acid of HCl is going to be in the burette. And the unknown solution, so the X molarity, NaOH, is going to be present in what I call the collection flask, or in the Erlenmeyer flask to be technical about it, but I call it a collection flask. And it will be located in the collection flask with a total volume of approximately 20 milliliters of solution. And I'm going to abbreviate solution as SOLN. All right, and so there's going to be a certain fraction of NaOH that is combined with water, all right, combined with water to make a total volume of approximately 20 mLs of solution. It's important for the student to realize that the actual amount of water here doesn't matter, all right? It doesn't matter. What matters is the moles of hydrochloric acid and the moles of sodium hydroxide. And going back to the hydrochloric acid, it's located in the burette, and the burette is graduated. Usually the burettes are going to hold a maximum of about 50 milliliters of total volume, but it's important to recognize that burettes come in all forms and sizes, and the size of the burette literally is going to depend on, in a technical way, on what the requirements are for the type of titration that you are doing. In most teaching labs, the total volume of the pipette is going to be 50 milliliters. And notice that we have this thing called a stopcock. It's very simple. It's just a valve. And what it allows you to do is turn the burette on or off so that we can conveniently add material into the collection flask where the NaOH is residing, and the collection flask is where the reaction is going to happen. Now, you need to remember a couple of things that I've pointed out in past videos about these strong acid, strong base titrations. The first thing is that the reactions are stoichiometric. And what that means is that they go to 100% completion. And that's important because what it means is that whatever amount of hydrochloric acid that we add into the collection flask, it's going to react unambiguously and to completion with whatever NaOH is there. All right. And the next thing is that the only two products that are produced are going to be water, which has a pH of 7, and a neutral salt, which has no effect on the acidity or on the pH of the final solution. Now, the aim here is we're starting with a certain unknown amount of NaOH that's in the collection flask. We don't know how many moles are here, and what we're going to do is we're going to add hydrochloric acid until all of the NaOH has reacted. So the point at where all the NaOH is gone has a special name. This is called the equivalence point. And equivalence point has a you know, this is a general definition, but I'm going to write it specifically for the reaction that we're dealing with here. So the equivalence point, this is the point where all the NaOH has reacted. Now, it's crucial for you to understand that at this point, the only stuff in the collection flask is water and salt. That's it. That's all we got in the collection flask at the very moment where we have dripped in the last itty-bit incremental amount of HCl at the point where the last vestiges of the NaOH reacts and is gone. And at that point, the only thing in there is going to be H2O and NaCl. So the pH of the equivalence is 7. So the pH of equivalence is 7. Now, here is the problem with running these kinds of reactions. We have got a colorless solution of hydrochloric acid that is being incrementally dripped into a solution of NaOH, which is also colorless. So the question is, how do we know when we've reached this equivalence point? So we have a problem here. Now, the way we solve this problem is we use what's called a color indicator. All right, a color indicator is a molecule that has specific colors at specific pHs. Specific colors at specific pHs. All right, and the one that we're going to use here is called bromethymol blue. Now, at the bottom of my screen here, I've taken the liberty of showing you a sample of bromethymol blue so you can clearly see what the situation is. And you can see that there are 3 flasks here. The flask on the right is the color of bromethymol blue under basic conditions where pH is greater than 7. All right, so the color is blue. And notice here that I colored the solution in the collection flask blue. I did that on purpose because when we start this experiment, the collection flask contains only NaOH and water. So the pH of the starting solution before we've added any hydrochloric acid is greater than 7. And so when you add the bromethymol blue, the solution is going to turn a nice sort of sky blue or dark blue in color. Now, I'm saying we add the color indicator to the solution. How much do we add? Usually you're going to add between 4 to 5 drops of the color indicator to the collection flask in a titration that happens in the laboratory. Now, the flask on the far left, the yellow flask, this is the color of bromethymol blue when the pH is less than 7. So this would be the color, which happens to be yellow, all right, under acidic conditions. So this is what bromethymol blue looks like if we had added the 4 or 5 drops to the hydrochloric acid that's actually in the burette. Then the solution would be yellow. And then notice the flask in the middle. It is green, and this is where pH is equal to 7. So we call the pH of the bromethymol blue at the end of this experiment where we have reached the equivalence point. We define a new point. This is called the end point. And this is the place where the color indicator turns to the appropriate color. All right, now, in the case of bromethymol blue, the color green is the endpoint. So we would say our endpoint for the above titration. So the endpoint here is going to be what we call the green endpoint. And it's where the pH is approximately 7. Now I say approximately, and in the case of this experiment, actually the endpoint is pretty darn close to the equivalence point. But technically speaking, and the student needs to realize this, is that the equivalence point, I'll put this over here, does not necessarily equal the endpoint. The whole issue is that the endpoint of the color indicator and the equivalence point of the reaction need to be suitably close enough together that you can actually use the endpoint to know where to end the reaction and actually shut the stopcock down and shut off the flow of acid into the collection flask. Okay, now I'm going to close this video here and we'll go to the next one in order to actually show how the application works and run some calculations.